All right, this is covalent compounds and Lewis diagrams. So Lewis diagrams, I'm going to talk to you guys about Lewis diagrams, and intermingled within the Lewis diagrams, I'm going to talk to you about what exactly a covalent bond is and remind us of what an ionic bond is and what it means. But the first thing about Lewis diagrams is they show how atoms are connected. What I mean by that, acetate. Wait, hold on. I can't spell. Acetate. Who remembers the formula for an acetate? Take a shot at it.
What's it? CH.
Jamie.
Wait, no, that's methane.
Okay, Jamie, what are you thinking? Whoa, lots of talking. By the way, I'm recording this, and you're talking. Jamie said C2H3O2 minus. Good. Does someone have another configuration of that? I think it was the one Brian was trying to get at.
Oh, I think it got it.
Yeah, what was it?
It was CH. 003.
Yeah, it's CH3. You're close. And then it was COO and then minus. So those are two different ways to represent acetate. One tells us a little bit more about how it's bonded together. Now a Lewis diagram, like why the heck CH3COO minus? That's a condensed Lewis diagram. Because a Lewis diagram looks like this, a carbon with 1, 2, 3 hydrogens around it, next to another carbon that's double bonded to oxygen and single bonded to another oxygen. And then we put these brackets around it to say it's got a spare electron flinging around. By the way, with note taking, just on a side note, why do I write these notes?
So we can take them.
Do I expect you, if I write, should you be writing?
Yes.
Yeah. If I don't write it, should you write more?
Yes.
I mean, if you have time. Yeah, right? Because I already go pretty fast.
Yes.
You know, this is my 5th lecture of the day. Why don't I just type it up and put it up there? So I allow you to process. Also, it slows me down. I already go too fast. I try to not go too fast. But if I write it, that'll slow me down so you can write it as well. Remember note-taking etiquette? You should allow your partners to look at your notes. That way if they get behind, they can see. It's not cheating in note-taking. It's being nice to your neighbor. This is where we're headed. Because you're like, what the heck, Vasquez? How did you even know to do that or write that? What does that even mean? This right here is a Lewis diagram. And if you notice, this is from the Lewis diagram. That's why they write it CH3COO. Instead of just the easier way to memorize it, Jamie and I share the same C2H3O2. It's 232. I feel like those numbers are easier to remember. But it doesn't tell us a lot about it. So Lewis diagrams show us how elements are connected. Lewis diagrams do not show three-dimensional shape. Because in that diagram right there, can you tell if the hydrogen is actually coming out at you or maybe behind the screen? No. Looks like one flat piece of paper, one flat screen. When in actuality, this is a three-dimensional compound. It takes up space in front, in back, on the side, all around. Next week, we're going to learn about shape, and we're going to learn about how to build a model. Well, I'll even show you how to draw a three-dimensional shape on a two-dimensional piece of paper. And finally, Lewis diagrams focus on valence electrons. We're doing a little note taking, Adrian. We're not that far behind. We just started, but maybe you can get started and catch up from Natalie or Olson, who's taking notes, or Sampson. So we're focusing on valence electrons. That's why I just went over valence electrons, but let's write down and remind ourselves about them. Valence electrons are the outermost electron. They are involved in bonding. We'll come back to bonding. And then finally, they're the outermost electron because they are at the highest energy. They're at the highest energy level. So let me remind you what I mean by that. We doing all right over there? Yeah? Okay. Let's look at sulfur. Sulfur has 16 electrons. How do I know that? Because what did I just do with my sulfur is atomic number 16. Therefore, it has 16 protons, which means it has 16 electrons. How do I determine how many valence electrons are in sulfur? Well, I would do its electron configuration. So 1s2, I'm going to do 2 in green, 2s2, 2p6, and then in blue, it's 3s2, 3p, 1, 2, 3, 4. So the highest energy level, when I say highest energy level, I'll highlight this in blue. When I'm talking about this right here, I'm talking about this number. It's the highest energy level, 3. If I'm talking about the number of valence electrons, I'll do this in like dark green. How's that? Or maybe purple. I haven't used purple yet. The 2 and the 4 electrons that are in the highest energy level are a grand total of 6 valence electrons. So when I'm talking about valence electrons, I'm not talking about all 16 electrons. I'm talking about the ones that are in the outermost. Now I'm going to draw one more picture that you recognized. I talked to you guys about Bohr's model, but if here's our nucleus, the first ring is n equals 1, right? And we've got 2 electrons in n equals 1. And then we'll make the second level green. How many electrons are in n equals 2? 8. We got 1, 2, 3, 4, 5, 6, 7, 8. And then in the highest energy level for sulfur, which we're going to make that blue, how many are in n equals 3? How many are there? 6. 6. 2 plus 4. We've got 6. So we've got 1, 2, 3, 4, 5, 6. It has not achieved octet. It has only gotten 6 in its outermost shell. The inner electrons are the red and the green. The outer electrons are the blue. Those outer electrons are what we call valence electrons. If you guys have forgotten, or maybe you wondered, we just got done with naming. Here's the symbol. What's the charge of sulfur? What's the charge? Like if I was asking you if it was bonding. -2. Why is it -2? Because it really, really wants 2 more electrons so it can behave and act like it's argon. And why is argon so special? Because Don reminded us, right? It's achieved octet. So if ever you wondered why is everything in that column? Everything, by the way. Oxygen, what's the charge on oxygen? -2. Why? Because it has 6 valence electrons. Sulfur's got 6. How many does selenium have? 6. How many does tellurium have? 6. They're all just 2 away from being a noble gas. So when I talk about this idea of charge, what I'm talking about is bonding. So let's do a little refresh about bonding. There are 2 types of bonding. We have ionic ionic, and do you guys remember the other type of bonding? What do we call it? Covalent. Good. We've got ionic and covalent bonding. Ionic bonding is between metal, nonmetal, right? What's covalent between?
Non-metal and non-metal.
Nonmetal, nonmetal. Yeah. So ionic, first of all, is between a metal and a nonmetal. That's one refresher. It's about the electrons, though. And the electrons are give and take electrons. So if I had a calcium bonding with a sulfur, we already said, what's the charge on sulfur? -2, because it's really trying to get 2 more electrons. Where the heck did it get these 2 electrons? Did it just like randomly wave its wand and it gets 2 electrons from the universe?
It got them from calcium.
It got them from calcium. Well, how many valence electrons does calcium have? It has 2. If it could give them away, instead of having 20 electrons, it would have 18, and it would get to be like argon. So if it gives away electrons, it's a +2. When it gives away its outer valence electrons, the 2, the shell right below it has achieved octet. So it gets to achieve octet by giving away 2. Sulfur gets to achieve octet by taking the 2 from calcium. So sulfur didn't just magically get 2 electrons. It got them from its friend calcium. Sulfur could have also hooked up with its friend sodium, but then it would need 2 sodiums. Sodium only has 1 electron to give. So if sulfur would have hooked up with sodium, it would be N2S. It would need 2 of those sodiums for every 1 sulfur. Therein lies the ratio. You guys are really good at that ionic bond thing. Well, you're getting better at it, right? With naming and figuring out the compounds. Speaking of, the retake of the quiz will be on Friday, and I'll go over it a little bit tomorrow. And maybe even after today's lecture, you'll kind of understand this a little bit more. You already are understanding more why the ratios are the way they are. The bond for this, then, is just CaS. You need 1 calcium to give 1 sulfur its 2 electrons. We know some stuff about ionic bonded stuff. We did a lab with this where we tried to melt it in a little tray, and then we tried to melt it. Staring contest right now? Really? 3, 2, 1, go. No. Anyways, we tried to melt it in a Bunsen burner flame. This bond that happens, the ionic bond that happens, is very, very strong. And we'll find things like we can never take salt and melt it in a Bunsen burner. It's just too strong of a bond. In fact, ionically bonded stuff, kind of nice if you have extreme heat. But hold up, the minute you put it in water, what does it do? It dissolves. And in fact, all of a sudden, it dissolves and it's like sulfur, peace out. I don't want to be with you, but cool, keep my 2 electrons. I'll be calcium. I don't want them anyway. We're going to split apart. We're going to swim around in this cool beaker of water. And that's how we know it can conduct electricity, because they are charged particles, which is why when I stuck the light bulb in the salt water, it actually lit up. It was able to conduct electricity. So put ionically bonded stuff in water, it separates. Put ionically bonded stuff in fire, it does not melt, it stays solid. So those are just some interesting properties about ionic. Yeah, Nick?
So the salt, salt charged.
It charged up the water, yeah. Yeah, it went into this form. And it didn't go back into its original just plain old calcium and plain old sulfur. It allowed each to be in that ionized form. Now the other type of bond is covalent. Covalent is between nonmetal, nonmetal. And this is where electrons are, it shares electrons. Now, there's 2 types of ways to share. We can equally share, or we can unequally share. We'll talk about what these mean next week, and I'll just introduce the name of equal versus unequal. If I equally share my electrons, we call this a nonpolar covalent bond. If we unequally share, it's called a polar covalent bond. Yesterday and the day before, when you were doing the simulation, remember the yellow proton and the little black dots were the flinging electrons? I don't know if you noticed, the electrons were flinging around the entire yellow thing. Kind of crazy, right? All over the place. Like around. They were like jumping like this, all around. But the minute that you started putting the 2 protons together, like you took your mouse and had them close in. So pretend like Alexa's a proton, I'm a proton, our electrons are flinging around, and all of a sudden we get a little closer. The electrons are now flinging, but just in this region. So we're now sharing them. And I liked what the simulation said. We're not actually sharing, we're fighting over it. It's like, who wants some more? Who wants some more? Now, if we unequally, it's like an arm wrestle. Maybe I arm wrestle Alexa and I almost win. Like I'm like this. Well, I've got more electrons, right? Maybe the electrons are randomly flinging. I'm sorry, I said I was stronger than you. Maybe she's stronger than me and I'm losing. But the electrons will fling around equally, or they will fling around a little unequal. Now they're still in this region, but a polar covalent bond is when they hang out by one element more than they do the other. Now it's not ionic. I'm not like, here Alexa, take my electrons. I don't want them. It's not that. It's still shared. So I now want to show you how to actually create a Lewis diagram and why things are shared. Bear with me. This is quite a bit of writing, and it's quite a bit of rules. But you're going to want these rules because as you make Lewis diagrams, you're probably going to reference them over and over and over. So the rules for how to draw Lewis diagrams. this not working? Uh-oh. Dang, it just froze. No? There we go. All right, rule number 1. We're going to calculate the total valence electrons. Calculate the total valence electrons in a molecule or polyatomic ion. I don't know if you haven't made this revelation yet, or if you were too nervous to ask, or you were just overall slightly confused, but did you guys notice calcium carbonate, that's an ionic bond, or calcium sulfate, or potassium cyanide? Those are all polyatomic ions, and those are ionically bonded stuff. But if you think about for a minute, sulfate, a sulfate ion is SO4. So you've got a nonmetal bonded with 4 oxygens, nonmetal. Isn't that covalent? What about carbonate? CO3 2-, it's nonmetal, nonmetal. Isn't that covalent? Cyanide, carbon, and nitrogen. Are you getting the idea? Polyatomic ions are covalently bonded things that are charged because they have spare electrons that then bond ionically with a metal. So when you're looking at compounds, they're not as simple as I'm ionic or I'm covalent. Maybe portions of it are ionic, maybe other portions of it are covalent. And you could go even further. Some are polar covalent and some are nonpolar covalent. When you know these type of bonds, you can predict and understand the behavior of the molecule. So what do I mean by calculate? Let me do an example. For example, and we could review too. What's the name of that? Phosphorus and bromine. Here they are. Non-metal, non-metal. So do I use prefixes or not? Yes. Phosphorus, what prefix do I use? What's 3 represented with? Mono, di, tri, tetra, which one? Phosphorus. Yep, phosphorus. And then you do the prefix in front, so it'd be tri. And then bromide. Yeah. With ide. How do I know it's bonded? Because ide is the end. It's like when you get married, one of you might change your last name. The other one doesn't have to. So phosphorus doesn't have to change its name, but bromine does have to change its name, right? So it signifies that these two are bonded. So the closest analogy I could think of is like how some people change their last name. Now, why does phosphorus, you want to change yours? You can, why not? My cousins actually both changed their last name when they got married. And they came up with a new last name. I think that's kind of a cool idea. It's very 2020. What would you change it to? I don't know. But it's like equality. For a long, long time, if you were a woman, you had to change your name. But it's 2020, so let's not do that. My cousin, she's... Yeah? Wait for it. Brady, wait for it. That'd be fun. How come there's not a prefix in front of phosphorus? Because it's just one. We don't put mono for the first one, but we put mono for the second one if there's only one. But
how would you explain, like, people ask, why don't we put like a number, or why don't we put a prefix for phosphorus? Would you just say it has no charge?
why? No, it's because there's only one of them and it's first.
Oh.
If there's one of them and it's second, you have to use mono. Yeah. All right, so now that we've reviewed naming, let's go back to what I'm asking you originally to do. Let's calculate the total valence electrons in a molecule or polyatomic ion. How many valence electrons does phosphorus have? Valence electrons. Has 3 in its P, right? 3s2, 3p3, so it's got a grand total of 5. We have 3 bromines. How many valence electrons does bromine have?
7.
7, yeah, because it wants 1 more. Good, it has 7. Don't forget PEMDAS. Multiply before you add. So 3 times 7 is 21 plus 5 for a grand total of 26 valence electrons for the molecule. If you looked up for even a second, you're probably like, wait, what? Where'd those numbers come? Here, I'll show you. P has 5 valence electrons. That's why we have the 5. The 3 is because we have 3 bromines. So we'll have to multiply the number of valence electrons for bromine, which is 7. Is that helpful to you? Yeah, you get it? The 5 is coming from phosphorus, the 7 is coming from bromine. Because we have 3, we have to multiply it by 3. Grand total 26 valence electrons. All right. Step 2. We need to determine the central and terminal atoms. Yes. Determine the central and terminal atoms. I think we know what central means. It's the center. But terminal, like if you have a terminal disease, you're going to die. Your life is ending. If you terminate your job, you quit or got fired. If you call on the Terminator, Arnold Schwarzenegger will kill everything in sight, right? Terminate, right? Means the end. So central and terminal atoms. The central atom, it's the atom that can make the most bonds. In your notes, leave a little space, like maybe an inch or so. The terminal on the opposite, so if central is the atom that can make the most bonds, the terminal is the atom that can only make 1 bond.
And that like destroys those bonds.
Right. So terminal means end or outer. Another way to determine what the central atom is, it has the lowest number of valence electrons. What one has the lowest number of valence electrons, P or Br?
P.
P, it has 5. Bromine has 7. So in this case, P is going to be our central. Bromine must be our terminal. I'm going to write this in red because it's a special thing. By the way, if carbon is ever present, it's the king. It will always be central, no matter what. If carbon is present, it is the central atom no matter what. It is the central atom. Why is that? Well, first of all, it has 4 valence electrons. It's kind of nice because On the front, the back, and either side, it can make bonds. It just so happens that there's plenty of carbon on this planet. Our atmosphere is made up of mostly of, well, a lot of nitrogen, but it has quite a bit of carbon dioxide in it. And because plants have the ability to take the carbon dioxide and turn it into stuff, we have life. I honestly think photosynthesis, photosynthesis, I feel like it might be the most important chemical reaction that there is, because it is plants' ability to transform carbon dioxide into us, into a cow, into a beetle, into, any living thing. Adrian, Olson, Sampson. We're almost done with our day. Let's finish. The next step is we're going to draw a plausible structure. Plausible. That means like the same thing almost as possible. It could be like this. I think it's plausible that it could go this way or that way. You're going to join the atoms. Is that good? Yeah. We're going to join the atoms in the skeletal structure. Skeletal is because it's the bare minimum. Skeletal structure by a single covalent bond. The word skeletal. I've been saying something wrong my whole life until I was like, I think this must have been maybe when I was 40, 41, something, a couple years ago. Have you guys ever heard the phrase, oh, I'll flesh out that paper later, I'll flesh out the project later, I have an idea, but I'll flesh it out later. My whole life I said flesh, you guys. Flesh, I'll flesh it out later, F-L-U-S-H. If you're with me and you think that that word is flesh, no, flesh is what you do to the toilet. You flush your waste down. It's flesh. So here's the thing. You have an idea, a skeletal idea. If you put all the nitty-gritty on, the meat, the skin, everything out, you're fleshing out your idea. Am I the only one that thought it was flesh? You guys, did you think it was flesh too? Yeah, I thought it was flesh out my idea. No, it's flesh out. If you're going to flesh your idea out, that means you're throwing it out in the toilet. If you're going to flesh it out, that means you are expanding it. In this case, our plausible structure, we're going to draw the skeletal structure, what it could be. We're going to flesh it out in a little bit. So our plausible structure, we've got phosphorus as our central atom. And we're going to put our 3 bromines and connect them with a single bond. So I'm going to write this right here is a single covalent bond. Do you know what that single covalent bond represents? It is 2 shared valence electrons.
Wait, the dash is the right?
The dash, yeah. So this one is 2, this one. They're all representing 2 shared valence electrons.
So each dash represents
2 electrons. 2 shared electrons.
4? 6.
6 total. Did you guys hear Alexa's idea or thought here? So that means there's 6 right now. 2, 4, 6 electrons are being taken care of. How many do we have total? 26 of them. which leads us to our next step, step 4. For each bond in the skeletal structure, subtract 2 from the total valence electrons. We're going to subtract 2 from the total valence electrons. So our grand total was 26. We subtracted 2, 4, 6 of them because we've taken into account those 3 bonds. So we have 20 electrons remaining. Where'd that 6 come from? 2 times 3. There's 3 little lines up there. There's 3 bonds. Yeah, good. Each one representing 2 electrons. So now what do we do with those remaining electrons? Now that we have a skeletal structure, remember I said we have to flesh it out, and that's the next part. With the total number of valence electrons remaining, or with the remaining valence electrons, first, complete the octet. Complete the octet for the terminal atoms. For terminal atoms. How many electrons currently are around the Br in the skeletal? Like just any one of those. This Br, like right here, how many are around the Br? Well, 2. It doesn't have 8 yet. It only has 2. So we're going to complete the octet by putting our remaining around our terminal first. Then, if there's some left over, we'll complete the octet for the central atom. So what do I mean by that? Let me show you. We've got our skeletal structure. This P has 2 around it. This Br has 2 around it. They're sharing. Now P has 4 around it, and this bromine has 2, and now P has 6 around it, and this bromine has 2. I have 20 valence electrons left. It tells me first complete the octet for the terminal atoms. So I'm going to take away, let's see, 2, 4, 6, 8, 10, 12. Then I'm at 14, 16, 18. I have distributed 18 of my 20 leftover electrons. So it tells me first complete octet for terminal atoms. Cool. Each of those bromines now has 8. Then complete the octet for the central atom, and I've got 2 more, 19 and 20. So look, this Br has how many electrons surrounding it? What about the line? 8. How about this bromine? 8. How about this bromine?
8.
Okay, how about the phosphorus? 2, 4, 6, 8. Each line is 2, 4, 6, and then 7, 8 for the dots. Each of these have octet. But hang on a minute. They came to the table. Bromine had 7. Phosphorus had 5, and now they're sharing, and all of them have octet. So that is what a covalent bond is. I don't have enough electrons, you don't have enough electrons. Well, how about our electrons? We share some. That's what I mean by sharing. And by sharing, I achieve octet, meaning I get 8 valence electrons around me. Let's try an example and let's use our rules, because that was long and tedious and a lot of writing. So let's try this example. It was on our test yesterday. It was carbon tetrachloride. By the way, if you put something like methylchlorocarbon, I don't know. I know you looked it up on the internet. Because we don't know that naming system. I don't even know that naming system. That's like some naming system for later chemistry. This is carbon tetrachloride. So, first step, number 1, what's it telling us to do? Calculate the total valence electrons. Let's do it. How much are in carbon? How many valence electrons does carbon have?
4.
4. Why? Because it's got 1, 2, 3, 4 in its outermost shell. I have 4 chlorines. How many are in chlorine? How many valence electrons are in chlorine?
7.
7. Why? Because I've got 1, 2, 3, 4, 5, 6, 7 in my outermost shell. So my total valence electrons is 4 times 7, which is 28, plus another 4. So I've got 32 valence electrons that I'm working with. Step 2, determine the central atom. Which one is the central atom? C, because it's carbon. It's the king. It's always the central atom. Besides the fact it also has only 4 valence compared to 7. So step 3, I will draw a skeletal structure. I'm going to do carbon with a chlorine, a chlorine, a chlorine, and another chlorine. Step 4, I've got to subtract the electrons that I did the bonds with. So we've got 2, 4, 6, 8. So let me go ahead and subtract them. I'm left with 24 valence electrons. Step 5, I've got to distribute my leftovers, first to the terminal and then to the central. So I've got 24. So I do 2, 4, 6, 8, 10, 12, 14, 16, and 18, 20, 22, 24. Oh, cool, I ran out. I didn't even have to put any on the central atom. But uh-oh, is it okay?
Yeah.
Is carbon achieved octet already? Each of those lines represents 2.
Oh.
Yeah, look, carbon has 2, 4, 6, 8. It only came to the table with 4, yet it's sharing with all the chlorine. And look, each of the chlorines are happy too. Do you see? Cool, huh? I think we will stop there. I'll show you what happens if you run out tomorrow.